Hi, everyone. In today's lesson, we will be learning about Pascal's Triangle and making connections between Pascal's Triangle and combinations. For those of you who have taken the 3U course, you will have learned a little bit about Pascal's Triangle, and the initial phase here might be a bit of review. Those who have taken the 3M course in grade 11 might not have seen Pascal's Triangle before. Pascal's Triangle has been around a long time. In fact, before it was called Pascal's Triangle, many cultures have actually known about the patterns and used Pascal's Triangle. Ultimately, our modern version was attributed to Blaise Pascal, who did his work in the 17th century. He was the one who discovered numerous patterns, especially those including organized counting and things related to that and probability. What is Pascal's triangle? Well, I've actually just drawn the first 5 rows of Pascal's triangle on the left there. Terms in Pascal's triangle are designated by T and R. So T for term, N refers to the row number. So you can see we have 5 physical rows of Pascal's triangle here, but we actually index the rows starting with 0. So the first physical row we actually call row 0, and then row 1, etc., etc. The R, the second index here, refers to the diagonal number. And just like rows, the diagonals start at 0. So this is diagonal 0. This guy is diagonal 1. And so that's how we refer to the terms in Pascal's triangle. So what I'd like you to do, again, here is the first 5 rows of Pascal's triangle. Can you have a look at it, especially if you haven't seen it before? Can you describe a rule to generate any given row in Pascal's triangle? And then when you have that rule, could you add the next 2 rows to the diagram? So if you want to pause and think about it, and then unpause when you're ready, or you can just follow along with me. The rule, loosely speaking, is very simple. You have 1s on the outside, and to get the next term, you add the terms above. So 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and then a 1 on the outside. And if we use that same logic again, 1 plus 5 is 6, 1's on the outside, 15, 20 in the middle, 15, 6, and 1. So if you got those, then good job. Pascal's triangle is a triangular array of numbers where each term is the sum of the 2 terms above it. In the case of the 1s on the outside, flip back for a second. In the case of the 1s from the on the outside, there's only one number above it. There's just the 1 above and to the right, or on the other side, there's only the 1 above and to the left. So we just carry down the 1s because there's not 2 numbers to add. There's just 1 that we just keep carrying down. So that's how we make Pascal's triangle. Each term is the sum of the 2 terms above it. There is a really strong connection between Pascal's triangle and combinations. You guys are going to investigate that now. Here's an array of combinations. Can you actually calculate those combinations and then see if what you get looks familiar? Maybe you see where this is going, but give those a go. Take a pause, do it on your lesson sheet, or follow along with me if you just want to get it done. So 0 choose 0 is 1, 1 choose 0 is 1, 1 choose 1 is 1. 2 choose 0 is 1, 2 choose 1 is 2, and I bet you can see where this is going. 3 choose 0 is 1, and then 3, and then 3, and then 1, and then all of those in the bottom row give you the same terms as Pascal's triangle. And that's actual really interesting property of Pascal's triangle is that all the terms are directly related to combinations. So that's something pretty cool that's maybe not obvious upon looking at Pascal's triangle. Now we have 2 ways of generating rows in Pascal's triangle. One, to get the next row, you kind of use that rule of adding the terms above, just to write that in a concise form, add the terms above. Or two, you can actually use combinations to get rows in Pascal's triangle. So I know you guys already used the adding terms above rule to get the row, the next row in Pascal's triangle. But if we were to use combinations, you would do 5 choose 0, and then 5 choose 1, 5 choose 2, 5 choose 3. And you're more than welcome to actually try these combinations out, and you'll see you get the numbers in that row of Pascal's triangle, row 5. One more thing to investigate that's going to have a connection to our organized counting and combinatorics is the row sums. Take a moment and add up the row sums in Pascal's triangle, meaning like what do the numbers in each row add up to? So obviously 1 adds to 1, but if 1 plus 1 is equal to 2, and what does the next row add to, and so on and so forth. I bet you'll see a pattern. Probably after the next guy, you might be able to see what's going on. So if you want to pause and try that, or if you want to follow along, you can. 1 plus 2 plus 1 is 4. 1 plus 3 plus 3 plus 1 is 8. There's a distinct pattern there. Those are powers of 2. 1 plus 4 plus 6 plus 4 plus 1 is 16. And that's another neat property too, is that the rows in Pascal's triangle actually add to powers of 2. And it's actually not surprising if you know that the terms in Pascal's triangle relate to combinations. Check this out, guys. Remember our problem solving with combinations. If you recall the scenario where we said had 4 coins and we had to make a subset. One way to do that problem was to, ask, well, how many ways can I choose no coins? And then how many ways can I choose 1 coin? And how many ways can I choose 2, choose 3, how many ways can I choose all 4 coins, and added those together, right? That's one way we did that problem. We got 16, and those combinations do give you 1, 4, 6, 4, and 1. But we also frame that problem in terms of the fundamental counting principle, where we could take a coin or leave it, and with 4 coins, that gave us 16 options as well. So knowing that those terms are combinations, it actually doesn't surprise us. So we get powers of 2, because that's how it works with combinations. So the big things you guys need to know about Pascal's triangle, besides like how to make it and how like the rows and diagonals are labeled starting at 0 and so on and so forth. The big idea is the terms in Pascal's triangle are directly related to combinations. TNR is the same as NCR. We've investigated that. So that would be something new for you guys who have seen Pascal's triangle before. And a consequence of those terms in Pascal's triangle being combinations is that the rows in Pascal's triangle add powers of 2. So for example, row 10, we don't need to actually make Pascal's triangle all the way down to row 10. We just know that the sum in row 10 will be 2 to the power of 10, or 1024. So those are the important takeaways you guys should know about Pascal's triangle. A really, really cool application of Pascal's triangle are with pathway problems in Pascal's method. So I'm going to go through a few examples with you guys right now. This is called a Galton board. You may have seen things like that if you watch The Price is Right. If you're sick from school, they have a game called Plinko, where you drop a chip down a little pegboard. In this visual, it's a ball dropping down on pegs, and the ball has an equal chance of going left or right. We can actually use Pascal's triangle to determine the likelihood of a ball reaching any given bin. Later on, we're going to analyze the game of Plinko and talk about how a contestant can give themselves a chance to win the most money. So first, we're going to find out how many ways there are to drop a ball to the bottom. So we are going to use Pascal's method here. I'm going to switch colors to something that'll stand out pretty good, maybe green. So here's what we do, guys. So we're going to have an entry above each peg. So there's one way for a ball to kind of reach here. You drop it in, and the ball can go left or right. So to the left of this peg or above the peg below, and to the right of the peg or above that peg below. We're going to have a 1 and 1 because there's one way to get here and there's one way to get here. And then in the next row, we're going to have 3 entries above each peg. There's one way to get there. There's one way to get to the right, like just going right and right. There's no other way a ball can get to that point. But for this middle slot here, there's two ways to come. A ball can go left, right, or right, left, giving two. And what we're doing is we're adding the number of pathways above, and you get the numbers in Pascal's triangle here. So above this peg 1, on the other side above that peg 1, 4 pegs will have 4 numbers above. There's 3 ways to get between these pegs and 3 ways to get between this pegs. Again, we're just adding the number of possible pathways together. And as you can see in this particular board, you do get the numbers in Pascal's triangle. So this is just kind of an exercise in recreating some rows of Pascal's triangle. So let's finish it off. The rows I'm doing right now are rows that we've done already together. And then 1, but we're going to go one step further. 15, 20, 15, 6, and 1. Now that gets you above the final peg. It has to make a left-right decision before going in the bin. So we're going to go one more time. We're making the 8th row of Pascal's triangle here. We can do these still by mental math. 21, 7, and 1. So this is cool. The numbers at the bottom here represent the number of paths that you can take to get to each bin. There's only one way to get to the far left and right bin, but there's 7 ways to get to these bins, and you can so on and so forth. So if you add those up, just by adding those numbers, or by using the rule that we developed earlier, in this case, because these are just the rows in Pascal's triangle. So you can add them up, or you can do 2 to the power of 7 for the 7th row of Pascal's triangle. But that should be 128. Yeah, there's 128 little zigzag paths for the ball to go to the bottom. If I may as well, this doesn't necessarily need to be written down on your sheet, but if we think about, say, where did this 21 come from? How did we get 21 ways to the bottom here? If you think about, so looking at the ball being dropped, it has 7 different kind of pegs to make a left-right decision about. To get to this bin, this one I'm talking about right here, what has to happen is that a ball has to go left 5 times and then right 2 times. Oh, I wrote down a 2 instead of writing an R. I'll erase that. So yeah, like any pathway that winds up in that bin, the ball has gone left 5 times and right 2 times. How many ways are there to arrange 5 lefts and 2 R's? Well, we know this from earlier. That's 7 factorial, 5 repeating L's, 2 repeating R's. And that is the very definition of 7 choose 2. Of the 7 moves, the different ways to go right, 7 choose 2. So you can see, again, a connection between Pascal's triangle, combinations, and now pathways. So having done that, there's 128 ways to get to the bottom. So we think of all the different possibilities, 128 ways to reach the bottom. Of those ways to reach the bottom, if we just flip back, 35 and 35, 70 ways there was for the ball to reach the center 2 slots. There were 70 ways, right? These are the center slots here. We did all the work on the previous slide, 35 and 35, 70 ways. So a ball dropped into this Galton board has a 70 in 128 chance of, which reduces to 35 out of 64, but has a 35 out of 64. That's over 50% chance of getting to those center slots. In our next lesson, we're going to be analyzing a more complicated Galton board, the Plinko board from The Price is Right, just using the same skill. So the method we just used to figure out the number of pathways to the bottom is called Pascal's method, and essentially it's just using the rule to generate terms in Pascal's triangle. So in words, the rule is to get like the to get a term below, you add the above two adjacent terms. So for example, putting this into just a specific example, just got to find my cursor here. There it is. So let's say, we're adding T6, 3. So the term in the 6th row, 3rd diagonal, plus the term in the 6th row and the 4th diagonal. What this notation just saying is that you get a term, when you add those two guys in the 6th row, you get a term in the next row, add 1. You get a term in the 7th row. And that diagonal number in that 7th row is going to match the largest diagonal number from before. You'll get a term T74. This idea of Pascal's method can be applied not just to a Galton board that looked like Pascal's triangle, it can be applied to a ton of different pathway problems. We're going to do some right now. We have actually done problems like this several different ways, actually, but we're going to revisit them in terms of Pascal's method. So we're going to find the number of ways to go from A to B. So I'll get it started, and then with these, it'll be helpful if you pause the video, try it yourself, and you can unpause to check in. So just watching me fill in these values. But yeah, we're starting at A, so we'll put a 1 there. And we're going to apply Pascal's method. So this is like we're kind of like almost making Pascal's triangle just tilted on its side. There's one way to get to each of these points, corners that I'm labeling right now, right? Like if you think about the number of ways to get to the bottom left, there's just one way. You just go all the way down. It's like Pascal's triangle. You're just carrying the ones down, and the same going to the right. But then the number of ways to reach this corner is 2, like down and right or right and down. And then there'd be 3 ways to get here, 1 plus 2. And so we're just adding kind of like neighboring terms. I can come from here and I can come from here. So I add those numbers together, 5 and 6. And so if you want to pause and finish it off or just kind of follow along, that's fine. In this example here, we are essentially recreating Pascal's triangle again. This does not happen all the time, as you will see as we do some more complicated examples. But for now, with a regular grid, we are just going to get the terms we see in Pascal's triangle. And then just got to be careful with my mental math here, actually. 21 and 35, that is 56. And then we get 126. There is 126 ways to get from A to B. Thinking in terms of previous days, just double checking our answer, to get from A to B, you would that's a combination of going right 4 times and down 5 times. And that's equivalent to 9 factorial, 4 repeating R's, 5 repeating D's. Now, if you do that calculation, you can verify we should get, if we did our math correctly, 126. I certainly hope so, or I'll have to do some editing for this video, which I don't want to do. 120, yeah, 126. And then remember, remember, that is also the very definition of 9 choose 5, or 9 choose 4. The number of ways to choose your 5 downs from 9, or your 4 rights from 9. So 3 ways to do this problem, but we've now got one example of using Pascal's method. Now, Pascal's method works all the time. These methods here only work with like vanilla cookie cutter straight regular grids. So let's move on. Let's do a more complicated problem. So here's an irregular grid. We're going to find the number of ways to get from A to B. We're going to start off the same way, and you might think the numbers, and they will be looking similar to the previous problem. We'll start with 1s all the way on these corners. There's only one way to get to any of these spots. And then there's 2 ways to get here. And so far, everything is just normal, just like the last example. 3, 4, 6, 10, 10, 20, 15, 35. And here is, so right now we're just applying Pascal's method. And at this point, here's where the similarities end. And you have to avoid temptation just to kind of copy down the entries in Pascal's triangle. Because of this irregular grid, there are 35 ways to get to this point here. To get to this point below it, Well, there's only one way to get there, and it's from that square above. So we just carry down the 35, and then we carry down the 35 again. Unlike the previous ones where we just saw entries in Pascal's triangle, 35s don't appear in any more rows in Pascal's triangle. Well, I guess except down to row 35. Um, but so, and in the same way, we get repeating 15s because there's only 15 ways to get to this point and to this point. And now we continue on using Pascal's method, but now the entries we get don't correspond to the rows in Pascal's triangle. We're going to get 50 and 65, 85, 35 and 85 is 120, 85 and 65 is 150, and then finally we get 270 different ways to get from A to B in this grid. And there is no easy way to do this one using combinations and repeating elements. We have to use Pascal's method. Let's look at another example, just getting more practice using Pascal's method. We can apply it to games we like checkers, for example. So this is more just like most games of checkers won't have just one piece and an opposing piece on the board. This is just kind of getting used to Pascal's method. So a checker can only move diagonally. However, a checker can jump an opposing piece diagonally. You can't occupy the same square, but you can jump it. So let's figure out the number of ways that our checker on the bottom can get to the top of the board using Pascal's method. So we're going to start from the bottom. And here we go. So moving up, there is one way. I might switch to blue just so it stands out a bit better. There's one way to get to those two squares. And then moving up to the next row, there's only one way to get to this square, one way to get to this square, but there's two ways to get to this square. So again, initially, a lot of times the numbers you get are just the rows in Pascal's triangle. We get 1, 3, 3, 1. You'll notice like it is impossible for our checker to get to these spots because it's moving diagonally upward. We're not allowing it to double back. Let's continue. There's one way to get to this spot. There's 4 ways to get to this spot. You can't land here. And there's 4 ways to get here. At this point, our entries will not correspond perfectly with Pascal's triangle. Let's work left to right again. So 1 plus 4, there's 5 ways to reach this square. Let's be careful with the next one. I can come from here, where there's 4 ways, or I can jump that piece with 3 ways. And there's 7 ways to get to that square there if you can jump a piece. In the same way, we have 3 plus 4. There are 7 ways to get to this square. And over here, we just have 4. We're just carrying up the 4. There is nothing over here to add, right? We're just carrying up the 4. And the final row is not so bad. We carry up a 5. Here we have 2 things to add, another 2 things to add, and 11. And if we total those up, the number of different ways to reach the top of the board, 17, 31, there are 42 ways to reach the top of the board if you can jump over that checker. So just an exercise in getting used to Pascal's method. Why don't you try the next one? Here we've got 2 opposing pieces. Can you apply the same method? And this time we're starting to the left side of the board. So if you want to pause and unpause when you're ready, that'd be great. Or as usual, you can feel free to follow along with me as I do it. So we'll start off applying Pascal's method. Everything's pretty straightforward so far. 3 and 3. Actually can't get here. I can come up from here. That's 3. Can't land on that square. This square here, I can only come from here. There's a 3 because there's no way to reach any of these squares. So there's no way to jump over. That's just copying down the 3. It's the only way I get there. And then I can jump over here and get to this square one way. Being careful of the next row, 3 plus the 3 jumping gives me 6. 3 jumping plus the 3 gives me another 6. These arrows are just my little visual tool to help me. You can add them or not on your diagram. 3 plus 1 is 4. We're kind of in the clear now, guys. And then copy up a 1. In the final row, we copy up a 6, 12, 10, and 5. So in this scenario, there's less. If you add those up, 15, 18, that's 33 ways to get to the top in this particular checkers scenario. Now, all of the problems we've done applying Pascal's method have been on kind of regular grids where there might have been like an L shape to it or some pieces to jump over, but they were basically rectangular. We can actually apply Pascal's method for networks that aren't rectangular or kind of in a set grid format. So we're going to do one example like that. So it's kind of a silly problem, but the idea of having a nonlinear grid is a really helpful one. So let's do this one. We are going, Little Red Riding Hood is going from her house to grandma's house. She wants to figure out how many different routes she could take to grandma's house, assuming she moves left to right. So she never doubles back on herself. We're going to apply Pascal's method. We just have to kind of be careful because, sometimes there'll be we'll be able to get to a point from 3 different spots. But let's just work left to right and just be careful. I think we'll be fine. So here we go. If you want to follow along. We're starting at Red Riding Hood's house. So we'll put a 1 there. Working left to right, there's 1 way to get to that spot. There's 1 way to get to that spot from left to right. And there's 1 way to get to that spot moving left to right. So already it's unlike Pascal's triangle because we have 3 ones. I would encourage you to pause the video and just try this one on your own, see if you can figure it out. There's no harm in trying and getting it wrong. You can always fix things up. But as usual, you can follow along with me too if you would like. To get to this spot here, I can come from the upper right or bottom right. There's 2 ways to get there. Looking down, can come from here and here. There's 2 ways. We have to be careful and just looking at the number of ways to get to each spot. I can see now that coming from this way or this direction, there's 3 ways to reach this junction. And now I'm able to figure out this spot because there's 3 ways from here. There is 2 ways from here and 1 way from over there. 1 plus 2 plus 3. There's 6 different ways to get to this spot on the route to grandma's house. Let's continue. 2 plus 3, 5 ways to get here. And we only have 1 more to go. I can get to grandma's house from this direction where there's 2 ways. From here, where there's 5 ways. From here, there's 3 ways. And from here, there's 6. So in this final spot here, we're adding 2 plus 3 plus 5 plus 6. That gives us 16 ways to get to grandma's house in this problem. So a really interesting problem. You can use Pascal's method for nonlinear questions. It's very helpful for communications technology, traffic planning, because most of our city streets are not a perfect grid. So this tool can be very helpful. I will say this too is what you will be eventually adding larger and larger numbers, the larger your grids are. So just be careful with the math. Use a calculator if you have to. If you notice an error in this video, maybe if I added 2 numbers wrong, feel free to send me an email and I can fix it up. Applying Pascal's method is, it's a straightforward idea, but to execute, you just got to be careful, make sure you act correctly, consider where you could be coming from. All right. Next steps for you guys. There is a PDF of practice questions on our online platform. These are the ones you can try. I have linked to a site where there are some video solutions, but please feel free to let me know if you need a hand with anything. Friendly reminder too, as far as the time spent on the course, if you're doing this lesson, you're pretty most of the way through Unit 2. But so that you don't fall behind, 70 minutes or so of normal class time, plus or half an hour or so at home of doing like practice. 100 minutes a day is fairly reasonable for a grade 12 university course. And so my suggestion would be to budget that amount of time on average per day during your week. to make sure you don't fall behind in the course. Again, I hope to hear from you if you need some help. Otherwise, we will see you online. Have a great day.